Hey guys, here's a video to show you how to find local max and local mins. We know how to do absolutes if we have a closed interval or if we're looking at it on a graph. And actually on the graph we can find locals as well, but we need to be able to do it analytically. So in order to do it, we do need the derivative, of course. Seems to be a pretty common theme. So we'll get our derivative. And that takes care of that. And we need our critical numbers. So we'll set that equal to 0. And there's nowhere where this is undefined, so I really just care about when this is 0. So I'll take out a 12x, x squared minus x minus 2. So this is 12x, x minus 2, x plus 1. So I have critical numbers at x equals 0, 2, and negative 1. All right, now here's the thing, and we did something like this before when we did like the snake graphs. You're going to want to set up a number line. I'll show you why. If you set up a number line and put in those critical values, not drawn to scale, and this is f prime, you're going to actually be able to tell when your derivative is positive or negative, which is important. When we did it for the snake graph stuff, the positive derivative meant the particles moving to the right. The negative derivative, negative value meant the particles moving to the left. Well, this kind of helps us out here too, because as soon as I know whether the derivative is positive or negative, I actually will know if the function is increasing or decreasing. If the derivative is positive, my function's increasing. If the derivative is negative, my function's decreasing. We actually call that the increasing, and not a very creative name, but increasing, decreasing test. Okay, so again, if f prime is greater than 0, that would be increasing. If f prime is less than 0, that would be decreasing. Okay, assuming it's differentiable, of course, etc., etc. So this is what we're looking for. So let's do the same thing we did before. Let's see, I want numbers less than negative 1, so like negative a billion. Negative a billion, that's negative. This is negative. This is negative. So that makes a negative. Right? 3 negatives multiplied together. Between 0 and negative 1, so like negative a half. Negative, negative, positive makes a positive. Between 0 and 2, so like 1, positive, negative, positive. And then bigger than 2, like a positive a billion, positive, positive, positive. So just from this number line, I can determine where the function's increasing and decreasing. So you would say something like, f of x is decreasing on, and then you just look for the negative. So it would be, negative infinity to 1, and, from 0 to 2. Okay, so that would be decreasing. And then of course increasing would be the other, the other version. But for the AP, they actually want you to not just say it's decreasing, they want to say why. So you would say something like, because f prime is, decreasing, so it'd be less than 0. So they want to see that. This right here is not good enough according to the College Board. They do want you to sort of summarize your results, sort of indirectly, using the increasing decreasing test. You don't necessarily need to write the increasing decreasing test. You just need to make that kind of connection. So we're decreasing on these intervals. We're increasing on the other intervals. So increasing on, and that's going to be from negative 1 to 0, and 2 to positive infinity. And then the reason, of course, again, is because f prime of x is greater than 0. So something interesting happens here when you notice that your graph changes from either decreasing to increasing or increasing to decreasing. Okay, try to imagine it just visually. You have a graph coming down, decreasing, and then all of a sudden it's coming up, increasing. What do you suppose is happening right at that moment? Okay, just try to imagine it. I don't know what this graph necessarily looks like. You could graph it on your own if you want, but all I know is it's decreasing here, and then it's increasing. Well, if a graph changes from decreasing to increasing, we're going to have a local minimum here. Now, it could be an absolute. I don't know yet for sure, but it's at least a local. If I go from positive to negative, if I go from increasing to decreasing, well, then I would expect to have a bump, at the top. Okay, and that would be a local max, local min. All right, so we have local min at, and the local min, so I would have it at negative 1, comma, and then I plug in negative 1 here, and I get 3 plus 4, 7, negative 5. Actually, I think it's at 0. Negative 1, 0. And at 2, oh boy, here we go. 2, 4, 16, 48. minus 32, so 16. Minus 48 is negative 32, plus 5 is negative 27. So I have local mins at negative 1, 0, and 2, negative 27 because f prime changes from negative to positive. This is actually using what's called the first derivative test. Okay, you're using the first derivative to determine whether or not we have a local min or a local max. So you know you have a critical number. You check to see if the derivative changes from plus to minus or minus to plus. If it goes from negative to positive, then you know you have a minimum. If the derivative goes from positive to negative, you'll know you'll have a local max. I could also have said there's a local min at these points because f changes from decreasing to increasing. That means the same thing. But you do need the because. And then, of course, we have a local max at, so that's going to be 0, 5, it looks like, because f prime changes from positive to negative. Again, or f changes from increasing to decreasing. That would work as well. So the increasing decreasing test is really just looking for pluses and minuses in general. The first derivative test, sorry about that. The first derivative test is where you actually find local maxes and mins based on your increasing and decreasing changing. Your derivative changes sign. Okay, if you look in the book for first derivative test, you'll see it says, f prime changes from positive to negative or negative to positive. That's what you're looking for. Okay, so that's one basic intro example to finding local max and min. Stay tuned for another example, and then we'll talk about concavity as well. Okay, see ya.